Chapter 12. Our Collective Brains. Surrounded by a sea of ice above the 75th parallel, the polar Inuit live in an isolated region of northwestern Greenland, at the farthest reaches of the Inuits' massive expansion across the Arctic. Reference Chapter 10. They are the northernmost human population that has ever existed. Sometime in the 1820s, an epidemic hit this population of hunters and selectively killed off many of its oldest and most knowledgeable members. With the sudden disappearance of the know-how carried by these individuals, the group collectively lost its ability to make some of its most crucial and complex tools, including leasters, bows and arrows, the heat-trapping long entryways for snow houses, and most important, kayaks. With the loss of kayaks, the polar Inuit became effectively marooned, unable to maintain contact with other Inuit populations from which they could relearn this lost know-how. As noted by the Arctic explorers Elisha Kane and Isaac Hayes, who encountered the polar Inuit while searching for Sir John Franklin, reference Chapter 3, these technological losses had a dramatic impact, leaving the group unable to hunt caribou, no bows, or harvest the plentiful Arctic char from local streams, no leasters. The population declined until 1862, when another group of Inuit from around Baffin Island ran across them while traveling along the Greenland coast. The subsequent cultural reconnection led the polar Inuit to rapidly reacquire what they had lost, copying everything, including the style of Baffin Island kayaks. Decades later, with their population again increasing, and with ongoing contact with other Inuit in the rest of Greenland, the style of polar Inuit kayaks gradually shifted back from the large beamy kayaks learned from the Baffin Islanders to the small sleek kayaks of western Greenland. Though crucial to survival in the Arctic, the lost technologies were not things that the polar Inuit could easily recreate. Even having seen these technologies in operation as children, and with their population crashing, neither the older generation nor an entirely new generation responded to mother necessity by devising kayaks, leasters, compound bows, or long tunnel entrances. These sophisticated technologies had evolved culturally over generations, and this process of cumulative cultural evolution had imbued these technologies with nuances that implicitly depended on subtle, or even counterintuitive, engineering principles. And, lest there be any doubt that they really needed these lost technologies, it bears emphasis that they immediately readopted all the missing know-how once they had been reconnected to the broader Inuit collective brain, which began when the Baffin Islanders happened by. This simple historical case gives us a glimpse into one of the secrets to our success, and our Achilles heel. Once individuals evolve to learn from one another with sufficient accuracy, fidelity, social groups of individuals develop what might be called collective brains. The power of these collective brains to develop increasingly effective tools and technologies, as well as other forms of non-material culture, for example, know-how, depends in part on the size of the group of individuals engaged and on their social interconnectedness. It's our collective brains operating over generations, and not the innate inventive power or creative abilities of individual brains, that explain our species' fancy technologies and massive ecological success. Even individuals facing a life-and-death situation with weeks or months to prepare weren't nearly smart enough to figure out how to make even the basic tools for survival, as we learned from Burke and Wills, Franklin's men, and the Narvaez expedition. Our collective brains arise from a number of synergies created by the sharing of information among individuals. Here's the idea, broken down into its simplest form. We've established that from a very young age, humans focus on and learn from more skilled, competent, successful, and prestigious members of their communities and broader social networks. This means that the new and improved techniques, skills, or methods that emerge will often begin spreading through the population, as the less successful or younger members copy them. Improvements may arise through intentional invention as well as from lucky errors and the novel recombinations of elements copied from different people. The biases in human culture learning mean that as transmission proceeds across the group and over generations, the numerous errors, recombinations, and intentional modifications that don't lead to greater success will be filtered out, while those that do will tend to collect and spread. The size of the group and the social interconnectedness among these individuals plays a crucial role in this process. The most obvious way that the size of a group can matter is that more minds can generate more lucky errors, novel recombinations, chance insights, and intentional improvements. To see this in starkest terms, consider how group size influences the chances of coming up with an invention, say using feathers to fletch an arrow. Suppose any one individual operating alone will only figure out, by luck or effort, arrow fletching only once in 1,000 lifetimes. The chance that at least one person in a group of 10 people will figure out fletching in their lifetimes is then 1%. So, on average, a group of 10 persons will take 100 generations to come up with this invention, 2,500 years. In a group of 100 people, at least one person will devise it 10% of the time in one lifetime. Consequently, on average, it will take 11 generations for the group to figure this out, 275 years. For 1,000 people, there's a 63% chance they will get it in one generation, and on average, they will figure it out in 1.6 generations, 40 years. If you can unite 10,000 minds, you will have fletching in one generation. Well, technically a 99.995% chance. So, bigger groups have the potential for more rapid cumulative cultural evolution, especially since these effects further compound when you consider that many inventions require combining several elements, so their rate of emergence depends on the slowest element. This, of course, assumes that the members of this group are sufficiently socially interconnected to other members of the group so that their improvements can rapidly spread through the group. The bigger the group, the more implausible this assumption is. To see the importance of this sociality, imagine that every person is a social island who keeps any insights he has secret from all others. What happens? Well, not much. Some individuals will make slightly better tools, but then they will die and their improvements will go with them. No fancy tools will emerge, and the size of the group doesn't matter. This is the case for most animals. Thus, along with group size, the degree of social interconnectedness is very powerful in generating cumulative cultural evolution, even more powerful than individual smarts. Consider two very large pre-human populations, the geniuses and the butterflies. Suppose the geniuses will devise an invention once in 10 lifetimes. The butterflies are much dumber, only devising the same invention once in 1,000 lifetimes. So this means that the geniuses are 100 times smarter than the butterflies. However, the geniuses are not very social and have only one friend they can learn from. The butterflies have 10 friends, making them 10 times more social. Now, everyone in both populations tries to obtain an invention, both by figuring it out for themselves and by learning from friends. Suppose learning from friends is difficult. If a friend has it, a learner only learns it half the time. After everyone has done their own individual learning and tried to learn from their friends, do you think the innovation will be more common among the geniuses or the butterflies? Well, among the geniuses, a bit fewer than 1 out of 5 individuals, 18%, will end up with the invention. Half the geniuses will have figured it out all by themselves. Meanwhile, 99.9% of butterflies will have the innovation, but only 0.1% will have figured it out by themselves. Keep in mind that the geniuses were 100 times smarter than the butterflies, whereas the butterflies were only 10 times more social. Bottom line, if you want to have cool technology, it's better to be social than smart. Now, suppose the invention mentioned is the bow and arrow, and the butterflies and the geniuses come into conflict over territory. Who would win, the smarter group or the more social one? It's unclear, but the butterflies would have a good chance, since they would all be armed with bows and arrows, but only 18% of the geniuses would. This cultural evolutionary process may also shape the learnability of the know-how and skills related to tools, technology, and practices. Over generations, the details, techniques, and protocols that go into producing complex technologies should, all other things being equal, tend to simplify in ways that make them easier to learn and more intuitive. This propensity suggests that larger and more interconnected populations not only will have a larger variety of more sophisticated tools and technologies, but also that they will have more learnable techniques for producing them. As our species self-domesticated and we became increasingly social, our collective brains would have expanded, making possible greater technological sophistication and larger bodies of know-how. However, remember that our species' ability to live in large groups, well beyond residential populations, still depends heavily on social norms. Under the influence of intergroup competition, social norms that effectively maintain internal harmony in ever larger groups would have spread. Institutions that expand social groups and help forge broad alliances through kin ties, naming practices, affinal ties, spousal exchange, and rituals would have expanded our collective brains, making them better able to culturally evolve and sustain more complex bodies of cultural know-how, including more sophisticated tools and weapons. To the laboratory. My graduate student, Michael Muthukrishna, and I wondered if we could capture the effect of social interconnectedness on the accumulation of skills in a controlled way in our psychology laboratory. We set up a transmission chain in which a first generation of naive undergraduates was tasked with trying to recreate a complex target image using an unfamiliar image editing program. They could then write up to 2 pages of instructions and tips for the next generation of novices, who would receive this written information, as well as the image created by their teacher or teachers from the previous generation. We repeated this process for 10 laboratory generations. Each participant's skills were scored by measuring the similarity between the image they created and the target image. Participants were paid in cash according to both their own performance and that of their students. We recruited 100 undergraduates and assigned them to one of 2 treatment groups. In the 5-model treatment, novices received images and instructions from 5 individuals from the previous generation. By contrast, in the 1-model treatment, novices received the image and instructions from only 1 teacher from the previous generation. Keep in mind that both groups were the same size, but those in the 5-model treatment were 5 times more socially interconnected. The average skill of each generation did not increase when people could learn from only 1 teacher. However, when they could learn from all 5 individuals in the previous generation, the average skill increased dramatically, from just above 20% to over 85%. In the final generation, the least skilled person in the 5-model treatment was superior to the most skilled person in the 1-model treatment. Social interconnectedness made everyone more skilled by Generation 10. In the 5-model treatment, participants were not just copying the most skilled teacher in the prior generation. They were actually integrating insights from the top 4 teachers, of 5, but putting relatively more weight on what the top teacher did. This is important, since by acquiring distinct elements from different people, learners can create innovations without inventions. That is, by recombining things copied from different models, novelties can emerge without individuals themselves thinking up a new technique on their own. This process turns out to be crucial for understanding innovation. Similar research, led by Maxime Darex in France, reveals convergent findings. In a computer task, participants had to virtually construct either a simple arrowhead or a complex fish net, which they could then use to go fishing. Fishing yielded a catch, measured in points, which could be converted to cash after the experiment. After each round of fishing, participants could construct an improved arrowhead or fish net. To accomplish this, they could look at other members of their group, see how many fish they caught, and potentially copy their techniques. They could also rely on their own wits, causal mental models, and trial and error learning. The task went on for 15 rounds in groups ranging in size from 2 to 16 men. During the 15 rounds, the arrowheads made by the larger groups, with 8 or 16 men, got much better, while those made by the smaller group remained equally efficient or got slightly worse. By the end, the performance of the arrowheads of the largest group, with 16 people, was 50% better than those in the smallest groups, with 2 people. Size and interconnectedness in the world. Of course, while such laboratory experiments permit us to isolate the causal effect of sociality, it's crucial to see if these processes are actually important and operating in the real world. To explore this, the anthropologists Michelle Klein and Rob Boyd looked around the globe for a natural experiment, one that would permit them to get good measures of things like population size and technological complexity. Continental societies were worrisome, since these populations are all interconnected to some substantial degree, and technologies are known to spread across ethnic and linguistic boundaries. However, in the Pacific, islands or island clusters provide a natural way to partition populations into discrete chunks. Unlike with continents, hundreds of miles of ocean between islands guarantees at least some degree of isolation. To standardize the type of technology compared across islands, the duo focused on fishing tool kits, which are a crucial part of subsistence technologies through much of Oceania. Using detailed ethnographies of these populations, the researchers obtained estimates for the size and complexity of these tool kits, as well as of their population sizes at the time of European contact. Since these islands were far from true isolates, Klein and Boyd also assessed each group's relative degree of contact with other human populations. Sure enough, islands or island clusters with larger populations and more contact with other islands had both a greater number of different fishing tool types and more complex fishing technologies. One chart shows the relationship between population size and the number of tool types. People on islands with bigger populations had more tools at their disposal, and those tools tended to be more sophisticated. Another team, led by the evolutionary anthropologist Mark Collard, found the same kind of strong positive relationship when they examined 40 non-industrialized societies of farmers and herders from around the globe. Once again, larger populations had more complex technologies and a greater number of different types of tools. These effects can even be observed in orangutans. While orangutans have little or no cumulative culture, they do possess some social learning abilities that result in local, population-specific traditions. For example, some orangutan groups routinely use leaves to scoop up water from the ground, or use sticks to extract seeds from fruit. Data from several orangutan populations show that groups with greater interaction among individuals tend to possess more learned food-obtaining techniques. Of course, young orangutans are lucky if they can access 2 or 3 models, and in some groups, Mom is the only one around to learn from. The point is, larger and more interconnected populations generate more sophisticated tools, techniques, weapons, and know-how because they have larger collective brains. The Tasmanian Effect. This approach to understanding cumulative culture, to explaining the sophistication of technology and the size of a group's body of know-how, has 2 other, less intuitive implications. First, if a population suddenly shrinks or gets socially disconnected, it can actually lose adaptive cultural information, resulting in a loss of technical skills and the disappearance of complex technologies. Second, a population's size and social interconnectedness sets a maximum on the size of a group's collective brain. The loss of adaptive cultural information can result from 2 different processes. The first is what we saw happen to the polar Inuit. A random shock, an epidemic, happened to strike the most knowledgeable members of the community, wiping out a chunk of their cultural know-how. Because it removed the kayak, their transportation, from their cultural repertoire, and they were already geographically very isolated, they went into a slow downward spiral as their populations began further shrinking due to the technological losses. This kind of phenomena may be common. In his 1912 essay, The Disappearance of Useful Arts, the famed anthropologist and psychologist W.H.R. Rivers recorded many such puzzling disappearances. In one case, all of the master canoe builders from the Torres Islands, a geographically isolated island cluster in the northernmost part of the Vanuatu archipelago, died out. As a consequence, the inhabitants became isolated for a time, since no one had the skill to construct something better than a crude bamboo catamaran, which was not sufficiently seaworthy to travel outside the local island cluster, and was of no use in fishing. The other process is more subtle and, I suspect, more important. If someone is copying the techniques and practices of a highly skilled and knowledgeable expert, they will often end up with a level of skill or knowledge that is less than that of the expert they are copying. Copies are imperfect versions of the original, usually. To see this, imagine a master archer who always scores 100 points on the archery test. He is tasked with training 100 novices. Suppose that by the time the master dies, all the novices have learned 95% of his skills. That is, they get 95 points on the archery test. One of them is then picked to teach the next set of novices, and so on over 20 generations. How good will the 20th generation be at archery? Not good. They will get only 35 points on the test. The reason is that some information was lost every generation, because copies are usually worse than the originals. Cumulative cultural evolution has to fight against this force, and is best able to do so in larger populations that are highly socially interconnected. The key is that most individuals end up imperfect, worse than the models they are learning from. However, some few individuals, whether by luck, fierce practice, or intentional invention, end up better than their teachers. To see this, let's rerun the Archer thought experiment and assume now that 90% of the novices end up with 80% of the master's skills. 10%, however, end up with 105% of his skills. The best among the novices is again picked to teach the next generation. How will the 20th generation look now? Excellent. After 20 generations, everyone will score over 200 on the archery test, twice the original master's score. Interestingly, the average score of the novices won't exceed the master's original score of 100 points until the 5th generation. This occurs because although 90% of the learners are still ending up worse than their teachers, the rankings of the teachers are gradually improving, and they eventually pull the learners along with them. Larger populations can overcome the inherent loss of information in cultural transmission, because if more individuals are trying to learn something, there's a better chance that someone will end up with knowledge or skills that are at least as good as, or better than, those of the model they are learning from. Interconnectedness is important because it means more individuals have a chance to access the most skilled or successful models, and thereby have a chance to exceed them, and so can recombine elements learned from different highly skilled or successful models to create novel recombinations. These ideas first struck me when I was reading about the Aboriginal inhabitants of the island of Tasmania. Roughly 4/5 the size of Ireland and comparable to Sri Lanka, Tasmania lies about 200 kilometers south of Victoria, Australia. When the earliest European explorers made contact with the Tasmanians in the late 18th century, they discovered a population of hunter-gatherers equipped with the simplest toolkit of any society ever encountered by Europeans. To hunt and fight, men used only a one-piece spear, rocks, and throwing clubs. For watercraft, the Tasmanians relied on leaky reed rafts and lacked paddles. To ford rivers, women would swim the raft across, towing their husbands and offspring. In the cool maritime climate, Tasmanians slung wallaby skins over their shoulders and applied grease to their exposed skin. Curiously, the Tasmanians did not catch or eat any fish, despite fish being plentiful around the island. They drank from skulls, and may even have lost the ability to make fire. In all, the Tasmanian toolkit consisted of only about 24 items. To put this simplicity into perspective, let's consider the Pama-Nyungan-speaking Aborigines who were contemporary with the Tasmanians in the 18th century and lived just across the Bass Strait in Victoria. These Aborigines possessed the entire Tasmanian toolkit, plus hundreds of additional specialized tools, including a fine array of bone tools, leasters, spear throwers, boomerangs, mounted adzes for woodworking, many multi-part tools, a variety of nets for birds, fish, and wallabies, sewn bark canoes with paddles, string bags, ground-edge axes, and wooden bowls for drinking. For clothing, rather than draped wallaby skins and grease, the Aborigines wrapped themselves in snugly fitting possum skin cloaks, sewn and tailored with bone awls and needles. For fishing, the Aboriginal populations used shellfish hooks, nets, traps, and fishing spears. Somehow, the Tasmanians ended up with a much simpler toolkit than did their contemporary cousins just across the Bass Strait. The Tasmanian toolkit is simple even when compared to that of many ancient Paleolithic societies. The archaeological record from many parts of the world, going back tens and even hundreds of thousands of years, reveals the emergence of more complex toolkits than those possessed by the Tasmanians at the time of European contact. Tasmanian stone tools are much cruder than many of the tools found in Europe after about 40,000 years ago, and are consistent with the stone tools made by many Neanderthals and even by more ancient members of our genus. The Tasmanians lacked bone tools, yet elsewhere finely crafted bone harpoon points date to at least 89,000 years ago. Similarly, stone points for spears date to 500,000 years ago, well before the emergence of our species. And even if we put this particularly old find aside, it's generally accepted that hafted tools date back before the origins of our species, 200,000 years ago. While Tasmanians were limited to one-piece wallaby skins for clothing and leaky rafts for water transport, the mere presence of humans in the Arctic 30,000 years ago and in Australia at least 45,000 years ago attests to the existence of both warm, fitted clothing and reliable watercraft that can cross open oceans. Consistent with this, humans in Indonesia were catching tuna, sharks, and wrasses in the open ocean 42,000 years ago. The puzzle deepens when we realize that Tasmania was connected to the rest of Australia until about 12,000 years ago. As the seas rose, the Bass Strait flooded and transformed Tasmania from an Australian peninsula to an island. Until this isolation, the archaeological remains left by Tasmanians cannot be distinguished in terms of complexity from those found in Australia. With their isolation, Tasmanians began to lose complex tools. The number of bone tools gradually dwindled until about 3,500 years ago, when they vanished entirely. As evidenced by fish bones, at least some ancient Tasmanian groups probably relied heavily on fish. One archaeological site that was occupied consistently between about 8,000 and 5,000 years ago indicates a fairly heavy reliance on fish, second in importance only to seals. But gradually, fish dwindle and disappear from the record. By the time Captain Cook's men offered freshly caught fish from the bountiful waters around the island in 1777, the Tasmanians reacted with disgust. Yet they gladly took and ate the bread Cook offered. Of course, life did not stand still on the north side of the Bass Strait. As we discussed in Chapter 10, during the millennia when the Tasmanians were losing their fishing technologies, bone tools, and fitted clothing, the Pama-Nyungan expansion was underway. From the north of Australia, this expansion brought to Victoria not only fancier stone tools, dogs, and seed grinders, but also new social institutions and communal rituals that more effectively integrated local groups into larger regional populations, creating greater social interconnectedness among the bigger overall population. This would have permitted cumulative cultural evolution to generate more sophisticated tools and more complex tool kits. But the Pama-Nyungan expansion never crossed the Bass Strait to Tasmania. By isolating Tasmanians for 8 to 10 millennia, the rising seas cut them off from the vast social networks of Australia, suddenly shrinking their collective brains. A gradual loss of their most complex and difficult-to-learn skills and technologies ensued. Their isolation also prevented them from acquiring the technological and institutional innovations that would have expanded their collective brain by fostering greater interconnectedness and fancier tools, weapons, and know-how.